Welcome to the 2021 HTEC National Conference Educator-Led Breakout Sessions. My name is Treon Giorgio, and I'm going to be your host for this breakout session. I'm going to talk about CNC Macro Programming. Now, if you remember our keynote speaker's speech this morning, we've got to start pushing the limits of what we can do with technology and CNC machines. So this presentation is going to show you how to perform macro programming. Now, I'd first like to kind of talk about how we're going to take care of questions and answers. You'll notice in the right side of the window right there, there's a chat or a Q&A session. My colleague over here, Auburn Hendricks, who's also a University Council representative this year, is going to be fielding the Q&A questions. So if you have questions as I go through the presentation, put them in that Q&A section. And if he can answer them during that time, he's going to answer them. But we're going to reserve answering the questions for the last part of my presentation. So I'm going to go through for about 30 minutes, 35 minutes, show you a video, and then take questions towards the end that Auburn couldn't actually answer. So Auburn, thank you very much for doing that. And just a little bit about how today's presentation is going to go. We're going to talk about macros. So if you've never seen CNC macros or you have no idea what a macro is, you're in the right place. Because I'm going to start from scratch on what macros are and how macro variables work. Then I'm going to start talking a little bit about how we can use these macro variables to create intelligent CNC macro programs in order to make our machines work with other pieces of equipment like robotics and so forth, or maybe just to inspect a part and make sure it's good before the machine's done. So after I talk about that, I'll go through a project. Now, I've provided a macro programming project, the one that I give to all my Cal Poly manufacturing engineers. And it's a class project that we use in our junior level curriculum for a manufacturing engineering program. And I'm going to go through and explain step by step how this project works. And you can take this project and use it 100%, or you can use elements out of it in order to teach macros within your program. Now, you're wondering, what are these macros Treon keeps talking about? Well, macros are any type of CNC program that adds capabilities and flexibility that's not possible with that standard G code. So G code was invented in the 1950s before computers, right? At MIT on the other coast. But, you know, they had relays at that point. So the code is very simple G code. It's block by block, simple instructions. It goes right in order. And when computers, as we've invented computers, we haven't really updated our G code except with macros right there. So macros allow us to integrate other manufacturing technology with the CNC machine tools. It allows us to do complex or intelligent machine motions. I can, based off variables in my control, I can branch off to different points in my program based off the data that I'm seeing at that time. Or I could perform lights out machining as well with these macros. Now, the whole key to the macros are variables. All a variable is a number. So it's a number representing some sort of data, right? And these variables are stored in a giant database, and the database location is called a register. So these registers have the data that we can use to read a value from a variable. We can assign a value to a variable. We can use these variables to evaluate an expression using these variables. Or we could look at a variable and conditionally or unconditionally branch to another point in the program. And I'm going to show you how all this works throughout today's presentation. Now, these variables, they come in 3 different types out there. So we've got local, global, and system variables. But no matter what type of variable we have, they are referenced in a CNC program with the pound symbol, maybe hashtag if you're younger. But the pound symbol is followed by a positive number, and that number is the variable number. So for example, variable 10,103 would be variable 10,103 in the next gen control. The legacy or the old control uses 3-digit variables. So the only difference between the next gen and the next gen control and the legacy control is 10,000 in front of the variable number right there. So that's the only difference. What I'm going to show you is in next gen control style, except for my calculations, but I'll show you that. But you can see I reference all my variables with the 10,000 number and then the variable number afterwards. So that's how we represent a variable, hashtag or pound, and then the number. Now, these variables, remember there's 3 different types. There's local, global, and then our system variables. The local variables, there's only 33 of those. they're actually used with the G65 statement. So maybe a lot of you have used probes before. G65, P9810, when you probe a bore, something like that. So that G65 statement needs to be able to pass variables back and forth in order to control it, right? So you can actually make your own G65 statements up and pass variables into the local variables registers in your G65 statement. So these local variables are nested and available for use only during that one single G65 callout. So let me explain a little bit more on how that works. So for example, I'm going to show you my program here in a little bit, or my project, my macro programming project. And the way it's going to work is the students are given sub-programs. We're going to talk about that. But the sub-program has macro variable numbers in it. So you'll see we have X is or #1, right, or #1, variable 1. Y is variable 2. So if I want to be able to address that macro sub-program that's in the control with a G65 callout, I can simply call out G65, the program number, P210, then A, B, C, I, J, K, I, J. So basically these variables back here will be sent to the appropriate register based on what it's in the G65 callout. For example, variable 1's A, variable 2's B, variable 3 is C. Then it just repeats IJK all the way through. So if I did a call up G65 P100 A1 B2 C3, the variables populated in the control will be 1/10,000th, 2/10,000ths, and 3/10,000ths of an inch. That's how local variables work. The G65 line populates 1 through 33. You can use one of them. You can use all of them. It's up to you. You're the programmer. So you populate those and use them in your program somehow. That's local macros. Now, global macros variables are general purpose data out there. So I can store data in the global macro variables and use it for logic. For example, I'm going to set my target variable, number 101, you can see that down there, as my target bore size for my part. We're going to be making a simple part here with this macro program. It's got a bore in the center and a five-hole bolt hole pattern around the outside. So I wanted to maybe do some logic to compare stuff. So I set a macro variable, a general one, to a certain number. You can see I also set a tolerance, variable 102 there. I set at 1 thou, that's a plus or minus tolerance. So I can use global variables to just as data. I can put data in there and use it for math. You can also use your global variables for your probes. So you got to be careful because you can accidentally overwrite some of your global macro variables, and that would be maybe your probe calibration or your measurement data. Now, coming up in a little bit in this presentation, I have a list of all of the variables in the Haas controls, so you can make sure that you don't accidentally do that if you start playing around with these macro programs. But like for probe measurement data, variable 188 is the feature size. It always is. So you can, whenever you probe, if you have variable 188 showing up on the screen, it'll always show you your feature size. Or I can go back in the control and use the registers to do math with that feature size, which I'm going to show you here a little bit about that here in a little bit. So right here off to the right, these are the different variables when I probe a bore with the Renishaw probe. If I wanted to see the true X position or the X position of where I was at, it's variable 185 right there. So you can see as we move through, I'm going to be showing you different variables and how they actually work. Now, the third type of variable out there is a system macro variable. So the system variables allow the basically program interaction with the controls settings. So I can basically look at I can look at settings in the control, such as like spindle load, and I could shut the control down if it went above a certain spindle load percentage if I wanted to, or shut the program down, have an alarm out. Or I could set tool diameters. So you're going to see in the program I'm going to give you here in a little bit, or the project, when we first start off, we want to make sure everybody's on a level playing field. So I force the offsets, the diameter wear for tool number 5. Basically, I set that to 0, so there's no wear in there. And then I also force the tool diameter size to the nominal size, even though the tool's been sharpened, which we'll talk about in a minute. So you can set your tool offsets through variables by simply doing pound 2405 equal, that should be an equal sign. It is about 0.625. I've now set my tool number 5 diameter in the offsets to 625. I didn't have to touch it on the probe or anything like that. So system macro variables are very powerful. And that's what actually makes this macro programming very powerful, because I'm able to look at timers, positions, and loads and perform actions based off what's occurring on the machine in real time. So some system variables are like switches. I want you to realize that, where they can just be basically turned on and off right there. And some system so like, for example, I could program alarm. I can turn on an alarm at any time and make it say whatever I want. So if I was to program in pound 3000 equals 1, that's a programmable alarm macro code there. So, and then whatever's in parentheses afterwards, it shows up in the alarm message. So if I needed to generate a custom alarm, I have the possibility of generating up to 999 custom alarms in that Haas control. So if I'm writing a macro program, I could tell the operator exactly why it alarmed out and stopped. Give him a specific alarm message. So that's an example of a system macro variable that acts like a switch. There's other system macro variables that are basically read-only. So they're used as data. So that's going to be example like your spindle load. You can't write a spindle load. That's based off of your surface speed, your depth of cut, your chip load, and basically in your cutting tool conditions, right? So that's going to be something that you can just use as data. The other ones are like switches. Now, those are the 3 different types of variables out there in the Haas control that we can use to program macros with. So let's review them real quick. So 0 is not a number. If you remember, 1 through 33 is going to be our numbers. 1 through 33 are our macro call variables. Those are the local variables that basically only work with the G65 code. They get populated when the G65 code sends those variables to the registers. Once the G65 is done, they're done. They don't get used again. It's just kind of like a one call only variable register. Then 10,000 through 10,999 are general purpose variables. So remember, there's some that you can use for math, like they recommend 100 through 149 are general that you can just use for math. You can put any number in there, it'll save it on power off. There's also 500 through 550 is another general purpose one that you should use. And then if you don't want to mess up like your probes and stuff like that, if you look down here in the 10,000, there are probe calibration ones right here. It's 10,550 through 599. So you got to make sure if you're using the variables and populating them, that you're not populating something the machine needs to go ahead and perform probing or something like that. But so looking on at these variables, there's the rest of them are system variables. So at any time, I can look up this data with my CNC program and do logic with it if I needed to. So I can look at feed times. I can look at my work offset. I can look at my x-axis location. I mean, every single piece of data in that machine is available for you to use in your macro program. And this is where I teach a lot of my manufacturing engineers where this becomes powerful is in the automatic tool management stuff. So these ATM macro codes allow you to basically write code behind the scenes to switch tools. Like, for example, if you do a broken tool detection, the machine is just going to alarm out. You don't want to do that because time is money. You want, if the machine's going to find a broken tool, you don't want it to just alarm out. You want it to go find another backup tool in the carousel in the pocket. So, and then switch to that one and then start timing that one. So you can do very powerful stuff with these macros, just like looking at these different variables out here. Now, you're probably wondering, geez, we learned about these 3 different types of variables and what they do and the differences, but how do we use all these variables to make our programs more intelligent, right? That's what it's all about, trying to make more parts quicker and get more parts out the door, be more productive, right? Think about that from the sewing needles this morning, right? So now, number one thing, when we are doing logic here, we want to turn our block look ahead off. So when we start to do macro programs and we're going to do a little bit of logic, the Haas control looks at 20, 25 lines ahead. I forgot the actual number, but it's looking ahead a bunch of lines. And if you're trying to do block by block logic, like this, it happens, then this, then that, you can't be looking 20 lines ahead and anticipating because you have to be line by line. So the first thing you do when you start macro programming is turn off your block look ahead to 1 block. If you start machining, turn it back on. But while you're doing the logic and basically figuring out where your program's going to branch, turn that block look ahead off. So that's G103. After that, you're wondering, how do we use these variables? I told you, if you remember, you use the pound symbol, right? So anytime you have the pound symbol in the number, that's the variable in your CNC program. So I could actually use these macro variables in place of a G-code address. And that's really the key to my CNC macro project. I'll explain a piece of it. So these variables and the variables at runtime will be used as the address variables in the G-code. So like right down there, if I have G99, this is right out of the CAN cycle from my project. When I have G99 X hashtag 1 or pound 1, Y variable 2, so it's going to go look in the register for variable 1 and variable 2 and use that when it actually runs this code. So the students have to figure out a G65 line to get all those variables correct to run it in the machine. So that's one way we can use macro variables. We can use them in place of a G code. Another place we can use them are in statements. So you know what a statement is, right? Not your bank statement. We're talking about math statements here, right? So there's operators, there's arithmetic, there's Boolean and logical operators, there's functions, there's statements and control statements. We just made, with macros, we made the CNC G code as intelligent as a regular PC or computer. That's what we can do. So we can go ahead and have it do logic. That's really important. But before we get to that, it's got arithmetic operators, right? So you've got those by now. Plus, minus, divided by. We got this one. So it'll go ahead and do math for you, right? For example, later on when I show you this project, we're going to calculate the bore's undersize. This is a Mark Terryberry one, right? He did this example in his tip of the day where he showed you how to change the cutter comp based off the bore size that you measure. So if the bore size that we measured, you can calculate how undersized it is and put it in a variable right there. So it does that. And then it adjusts the wear offset based on the undersize. So you can do math with these variables and have things adjust in the control. Arithmetic operators. You can also do Boolean macro operators or Boolean operators here, right? These are really cool. It's either true or false. Or equal to, not equal to. So that's how they evaluate. It's either true or false is how these statements evaluate, right? If you remember programming from back in college. But we got equal to, not equal to, greater than, less than, and so forth. So for example, if I want, in my macro programming project that I'm going to show you here in a little bit, if I wanted to skip over probing the bolt hole circle pattern the second time, let's say I probe the bolt hole circle pattern, then I go probe another feature like a center bore, and then my center bore didn't work and I recut it. I don't want to come back and check to see if the 5 bolt hole circle pattern is still good because I already did that and time is money, right? So I could do an if statement. I could turn like a switch on after I probe the bolt hole circle pattern and I could say variable 103. If that's equal to 1, skip probing the bolt hole circle pattern and go over to this next line of code. So literally I was able to skip a measuring cycle because there was a 1 in my 103 variable, 10,103 variable. And if there's a 0 at the beginning of the program, it's going to probe the bolt hole circle pattern. So these Boolean operators are very powerful. It allows you to figure out, hey, do I want to skip that or where do I want to go? It allows you to introduce logic to the thing, right? Now, there's also logical macro operators. Those are a little bit advanced for today. We're not going to worry about those, but there's and, NAND, or, simple stuff, basic stuff you can still do with your computer, right? So logical ones, we're not going to spend much time on that slide. Now, it'll also do functions. We're not going to spend much time on functions either. But if you need to do sine, cosine, tangent, and so forth, it'll do that for you. So it'll do all of those basic functions, round, fixed, and so forth. Now, this is where the control statements get really powerful, right? So we're able to now control our program with macro. Can't do that with basic G code, right? G code goes block by block by block. I can't jump over here, then maybe down here based off what I see. But you can do that with a conditional execution. So there's two different types of control statements in macros. I can do an if and then statement, if this, then that, or I can do an iteration looping. So basically, traditional G code allows you to loop, of course, with an L address and an M99, but macros allow me to do a while, do, end construct. What that means is I can turn something on while something's active in the system, in the variables in the system. And then when the variables in the system say, hey, we've done this, I can turn that piece of the program back off. That's very powerful. That's a lot different than just M99 and the looping stuff. But these conditional executions, that's what we're going to go ahead and talk about today. So they actually allow you to branch off based off of a condition, right? Now we know that an unconditional branch in a CNC, you can do it two different ways. You could do your M99 P number, and that's going to branch to a certain point in your program. Or you could do a go-to and then a line number, and just jumps to that line number. I'm more of a big fan when I'm doing conditional branching to do the go-to. But you could do it either way, as you see down there. I'm just, for some reason, I think it has to do with back in my I only took Java class, but now we're off topic. But anyways, I just like the go-to for some reason over the M99 for conditional branching. M99 other stuff, I use it for jumping, looping, and returning. But for conditional branches, I'll say go-to and then the number, and then it'll jump to that line. So the way that thing works is I'm going to show you a project here that the students have to machine. Once it's machined, the macro program has to branch three ways based on the bore size in the center of the part. One way, if it's too big, it'll go ahead and say hole too large. Can you make it? If you cut a hole too large, you can't re-weld it up and machine it. It's not, well, you could, but we're not doing that. So it's got to jump to an alarm, right? Into a sub-program and call out an alarm, bore too big. Well, if the part is too small, I can recut it. And there's a good tip of the day video on how to do that, right? That's part of that. But if it's too small, you can go to 4,000 and jump to recut subprogram. And so I'm going to show you how that works here in a second. So you can go recut and then come back and remeasure and make sure you're good. Then if those two if statements, so it goes line by line. If it's false, it goes on to the next line. If it's false, it goes on to the next line. So the third choice is the parts intolerance. We're good. We're golden. So T1, M6, G28, Y0, M30 sends it back to the original tool, sends the table forward, we're done. So that's how you can branch off there conditionally based off sizes you've seen on your bore and go back and recut. Now, that leads me to explaining how my CNC macro programming project works. And then we're going to explain how the macros work step by step. And I think it's going to give you a better understanding of how CNC macro programming it works. So what we have here is this is a junior level CNC class. It's their third CNC class in their curriculum, actually. As freshmen, we bring them into this Gene Haas material removal lab that you've seen right behind me here. And they're operators. They learn how to load parts, machine parts, inspect them, and basic stuff with the machine. And then in their sophomore, junior year, they take a basic CNC programming class there, the IME 335, which both Professor Waldorf and I teach. And basically that they learn either Mastercam or HSM Works in that class, or Fusion 360, whatever CAD CAM they want to use. And then they're basically off to the races. They do mill and lathe basics. Then there's a 336 class, which is CNC macro programming and multi-axis programming. So we do 4 and 5 axis stuff, live tooling, lathe, and then the macro programming. So this is a 2-week project I give to my engineering students, and they have to manually write a CNC macro program. So they're writing it by hand. There's no CAM whatsoever involved in this project. Sorry, CAM companies. But what they're doing is they're going to machine the part and inspect it. They're given basically 3 programs in the control that they have to talk to. They're given a program 200, a 210, and a 220. And they have to make that part that you see right down there in that drawing. It's a 3x3 block that's 3/4 inches thick. And they have to go ahead and drill the 5-bolt hole pattern and then circular pocket mill that. Now, if we look, it's hard to see the tolerances on that, but the center bore on that thing's plus or minus 1 thou. And it's got a true position tolerance, I think, of 3 thou on that one. And then there's a true position of 10, and then 8 thou size tolerance on the bolt hole circle pattern right there. So they have to inspect that with the Haas probe and alarm out if it's out of true position, because you can't fix that if it's out of true position, and come back and fix it if the bore size is too small. So that's their job, is they have to write a program. And they're given 3 tools to do this, and actually 4, because the probe is technically a tool, right? So they're given a 1/2-inch end mill. They're given a 21-30 seconds carbide drill. I have a bunch of those donated. That's why we're using that carbide drill. Realize you could do this project with any type of tooling. You just got to change your feeds and speeds a little bit and your size of your tools. That's it. And then tool 5 is going to be a non-center cutting high-speed steel end mill. It's a beat down end mill that's been sharpened. You'll see that here in the video. So they've got to take those tools and make this part. But their goal is to make this part with the sub-programs I get them. So it's teaching them how to call sub-programs up with like external sub-programs, teaching them how to do G65 at the beginning, and then write macros to write probes. So they're given this program 200. And by the way, everybody has all of this information. It's in the handout section in this presentation. Or you could email me and I'll send you a zip file of it as well. But that program 200, all it does, if we look back at it real quick, the drawing is it trims up the sides right there. So it's going to trim up the sides with this program 200. It calls up an M98 P200, runs this program, probes it, finds the center of the part, and then trims the sides and gets it to the right size. After that, the students will have this drilling sub-program in the control, a P210 program, or 210. They're going to call up G65 P210. And notice this drilling sub-program drills a hole in the center and then a G70 bolt hole pattern. So they have to figure out these variables 1 through 8 and send them to the control using a G65 call out. So literally they drill this hole with one line of code because they call up this sub-program. Hopefully all the feeds and speeds and everything are right in the variables. And then they drill that thing. Then they're going to go ahead and circular pocket mill the part. So they're going to use a G13 to do some climb cutting. And they're going to climb cut a pocket in the center by sending the G65 macro variables to the control. So notice we have pound 1, variable 2, variable 3 and 4 all the way through here. So they send those variables to the control and hopefully drill the correct size, or not drill, mill the correct size pocket. The thing is, they think they have a 5/8 tool. Treon gave them a sharpen tool. They had no clue. So then when they run that sharpen tool, their bore size is going to be oversized. Or undersized, sorry. So they basically what they do is they have to get those probes out and then write custom probe macros to come in and measure everything on that part. So I teach them how protective positioning works, how to go ahead and come down and drill basically how they have to come down and measure the bolt hole circle pattern. There's actually a macro that measures bolt hole circle patterns with that probe. It's not in the quick code, but it's actually in the Renishaw manual. I'll show you that here in a second. So they measure the bolt hole circle pattern and test it for true position and size. Then they also come out and measure the center bore's true position with the probe. Then they take that size variable and they have to figure out which way to branch in the program to make that part work. So that's really the project. And I've made a flow chart of how my programming, so basically I gave you all the answers. So programs 200, 210, and 220 are going to control. Programs 337, which I gave you, is the answer that the students would write and create. The good thing is the answers are now out there on the internet, right? My project's changing next year. I've done this one for 3 years. So my project's changing ever so slightly next year. That's why I'm handing this one out and broadcasting the answers step by step. But your goal would be to take this, learn about macros, and maybe implement macro programming into your curriculum, because that's the next step, right? We can't be just cranking handles for the rest of our lives. We got to advance manufacturing. That's our job as educators. So with the students are tasked off with basically that problem statement. So the problem statement's actually also in the handouts as well. So the project, an overview explaining all of the constraints and criteria that their program must fulfill, that's in there. Now, their first step after they go through and they get the constraints and criteria is to come up with a flow chart of how their program is going to work, right? They're engineers. They're figuring out how we're going to solve this problem. So they have to put it down on paper first, come up with a flow chart. The flow chart is provided in PDF for you as well. And so I just provided a couple, like the oval, the parallelogram, the rectangle, and the diamond. That's all we need on this one. But you're going to see it steps through the program. And I actually stepped through the program right here with my flow chart in this 5-minute video. The link is right here in the PowerPoint, just so you know. But I have the video right here. So let me go ahead and play this for you, and then we'll take questions. So here we go. All right, we're ready to start the macro variable program. Before we start, notice right now that the diameter wear offset's got a negative 70 thou in it from the last time we ran this one. So the first thing that we do is we clear everything back to original in our program, just to let you know by switching our variables back. But when I go ahead and press cycle start, here we go. Cycle start, it goes to M98. P200, and it goes and grabs the external subroutine program that goes and grabs the probes. That external subroutine program probes the x-axis first right there, finds the center datum right there, and then it probes the y-axis right there, and it finds the center datum. So we now know that everything's based off the center of that stock at that point. Then we're going to grab that 1/2-inch 3-flute carbide end mill and trim up the sides real quick. We have a tight side tolerance there, right? So we have to trim up the sides. The soft jaw is actually relieved a little bit lower than where the part sits. And we're able to mill the sides with the periphery of the cutter. Back to the program, the main program. It calls up a G65 P210, which is a drilling program. So now we're G83 drilling. Now we're G70 drilling a bolt hole circle pattern. So notice those variables in there, right? There's no numbers. It's grabbing those variables from the G65 callout, the 1 through 33 local variables. So it used those A, B, C, I, J, Ks to populate this and drill those 5 holes. Wow. Didn't even have to have code. Well, we have to have code. Didn't even have to have numbers in our code. We use variables. So at that point, it just finished drilling all 5 holes. It's now on to the G65 P220 subprogram, where it pulls up a G13 pocket milling, and it grabs D5, so it grabbed that original diameter that got cleared out. Notice there's no wear in it at the moment. So we have 0.625 diameter right there with no wear. It thinks it's a 5/8-inch cutter. It's actually not. It's a 3564, so I pulled it out of the drawer. It's pretty beat up, so we'll see how well it cleans up this bore. So now it's bringing in the probe. It turned the probe on. These are all just handwritten ones, right? And it's going to probe the bolt hole circle pattern first. And if you look, the bolt hole circle pattern is being checked for true position, and it's being checked for size tolerance with those variables in there. If you look, we have our H and our M variable right there. So that H and the M variable will be our size and our true position respectively. When it's all done probing the holes, and assuming it doesn't fail or turn on an alarm at this point because it's out of size, it's going to come back and it's going to want to it's going to want to probe the center bore for the first time. Let it finish up this last hole that you see right here. And now we're going to pop back to the center bore, assuming we passed. We passed. We're down in. Now on this time, notice down here we have no size. So variable 188 is our size. Right now it's a nan because it doesn't know, and it's a 929 that cut that diameter. So that 35/64 end mill wasn't really a 625. And if we go up now on our offsets, it subtracted 70 thou out of the wear. The thing is, this end mill is pretty beat up. It might have to do this twice because I think that's a big cut for it. It's at full depth because this was supposed to be a finished cleanup pass, by the way. So remember, because it cycled different variables for the finish pass. So let's see what it comes out to now. I bet you it might have to cut it one more time. We'll see. That's just a high-speed steel dull end mill that we used for this project, for this demo. So it's coming down in. It's going to measure the bore one more time. Notice it skipped over measuring the bolt hole circle pattern because we turned that switch on in our macro program. So it's going to come up. What did it come up with? Ooh, 997.3. So we're like 3 thou out. We're only plus or minus 1 thou. So we got to come back and recut one more time. Hopefully it does it. It took 3 more thou out of the diameter wear right there. Check that out. So let's see if this does it this time, this last finish pass. All right, let's see. It's going to switch back to the probe. The probe's coming down. Here it comes. Rapid down. Gotta love these VF2 super speeds. Love that rapid. And it's now slowly feeding into the hole, protective positioning. And we are measuring the hole. Let's see what we come up with down here. We have a nan at the moment. And we're 1 inch and 4/10 thousandths. We're within tolerance. We can sell our part finally. We didn't have to pull it out of the fixture and scrap it. So this is really the step to lights out machining, right? Macro variables. Macro variables are very important. It should be a topic that we should all be introducing our students to, especially engineering students who are dealing with CNC.
Hey, Treon, you're still muted.
Oh, thank you very much. So basically, you have every single step needed now in order to run this program if you wanted to try it out or at least learn macro variables. So what I thought we would do is I would just go real quick, just the flow chart on like M codes that you need and what you can teach your students. Then I'll spend the last 5 to 8 minutes doing an actual quick Q&A session for everybody. But if you remember, that first startup was an M98, right? So an external subprogram call. So that's right there in the flow chart. All they had to do is M98 P200. It called up that program 200. It trimmed the sides, and it basically probed the center of the part. Now that I gave you the soft jaw as well in the handouts. So as long as you put the block in the center of or you cut the soft jaw, as long as you put the block in the center of that's the same size as the block. So if you basically have a little stick out, it trims those sides right up there. Then what we have is G83. We all probably know how that CAN cycle works, except the secret on this one is their G83 is a P2, their program 210 has all variables in there. So they have to figure out how this G65 line code will work in order to send that to the control and run program 210. So they're figuring out how to do this piece right here, that G65 line of code. Then the G70 is a bowl hole circle pattern, right? So that just adds in there that part of those variables, like the 5, the J of 5 is actually how many, is actually how many we have. So then the G13 circular pocket milling, I'm going to kind of go quick through that one. That one, you're allowed to do roughing passes or finish passes. So when the students first rough it, they have to send a G65 variable to rough at different depths of cut, right? Then, if they have to come back and do a cleanup pass, they use this same program, but they just program it in to just do a finish pass in their code. So they get to use this one twice in their programming or their code there. Then M99 is nice because that's how I return, right? Jump or loop or return. So M99 will do that for you, or the GoTo will do it as well. So that's another review of that one. If you're programming your probes and you're turning by hand and you're writing in there, you want to turn the probe on, number one. You've always got to spin it on. This happens automatically in the G65. If you use the visual quick code to do it, this automatically happens internally. You don't see these other macros being used. But spin on and spin off happen. If you're running it by yourself, you got to turn on, turn off, or else your batteries will go bad. So those little half double A's. Then if you're moving your program around the machine, this is the safest way to move it in protected positioning. Anything bumps that stylus, it's going to stop and not break the stylus. So we always run around in G65 P9810 and protected position around everywhere we go. Then to measure, this might be a new one for some people. You can measure a bolt hole circle pattern with the probe. And if you put the H value in and the M value in, it'll test tolerance and true position of that. So you can actually test your tolerances and your true positions in your program with your probe, and it'll alarm out if it's out of true position. So I did that one. And then the M9814 is the bore. You're probably used to this one. This one, I only tested for positional tolerance in this one. The reason I didn't do size is it would stop the program there and not let me do any type of conditional logic or any kind of conditional statements afterwards. So you're probably wondering, well, after we probe, all that logic, that seemed really confusing to me. Well, really, it's just setting variables, if you think about it. So if we look right here, it goes to variable 1 is the size of the hole. Then we've got the tolerance of the hole. And then we just do the logic. The if it's bigger, go flunk it. If it's smaller, go recut it. If it's the right size, send the table forward. We're done. That's all the logic has to do right there to branch those 3 different ways right there. So, and then in order to recut, this is how it recut. If you look at it, it jumped to this line after the regular M30 program. It jumped to 4,000, and it did its little math here, adjusting the undersize and the wear offset. Then it just called up a G65 with different variables to cut it at full depth. It cut it at the full 7.5 depth this time. And this is the key to not coming back and testing the whole circle pattern again. You turn a variable onto 1, it'll skip it next time if you say, hey, if this is equal to 1, go on to this next line where you skip that one. So that's really how it works. And the last but not least, if you have to program in an alarm at any time, pound 3000 equals 1, 2, 3, and you number between 1 and 99, put it in parentheses what you want it to say. My students have fun with this one, but only appropriate for school though. So that's pretty much my CNC macro introduction and my project. If you look, I've condensed the program. This is the entire program that ran that right here, the macros without comments. What questions do you have for me, everybody? Auburn?
So Sal has a question for us of, just to be clear, testing is true position by probe.
No, so I got that. So no, Sal, you can test true position in the older control too. So that's just a probe variable. Let me go back up to my slide there to answer that. So that's so good. You learned something new today. So there's optional variables you can put in your callouts. I don't have a list of all the optional ones right here. If you got the Renishaw manual out, you would definitely see that. By putting H in there, it's not normally in there, you will now test the size. So H, let me go to my actual program where I show that. So moving up, you can see when I go to probe, let me go all the way to the back. You're going to see I put in a G, or the G65, and that P line, there's going to be, here, it's right here. It's hard to see, but you'll see I have an H and an M. Let's see. I can't mark it up right now. But in that G65 line, there's an H value and an M. I added those externally to go ahead and just check that true position or that actual size. What other questions do we have? Sorry about the feedback in the video. I even told all of the other presenters not to do that, and I did it myself. So anybody else got any other questions? We got about 4 minutes left for questions.
Manuel was asking or noted that he didn't see the YouTube video up. When will that be available?
The YouTube video will be available. So that it's available right now, just the YouTube video, if you wanted to see that, or if you wanted to see the whole presentation, that will be available really soon. Let me get the video, the link to the video in the chat here in a second while you bring me up some more questions. Sound good?
Macro variable program.
Let me remove that one. And I'm gonna get the link to that while you guys ask other questions. Anybody else? So quiet. How many people do we end up having, Auburn?
I do not have a final count. So once we got going, I lost our count. So I'm not sure. I know when we started, we were at 48 people attending. So thank you guys all for attending.
Yeah, so I think that should be the YouTube link to my video that I was just watching on the actual project part right there. So I think that should help you out, Manuel. Anybody else? Well, we have about a 15-minute break then, and before we go off to the rest of the presentations. So with that 15-minute break, Eric, just so you know that you're going to be able to see everything. So you're going to be able to see everything. This has been recorded, so you can go back and watch this. It'll be available on this Big Marker channel until December. I'm also going to be taking the recording off and putting it on my own YouTube channel, so you can access it at any time. There's also been a question, Christopher. Good to see you, Christopher. He asks about some people criticizing using the same machine for cutting and inspection. Can you comment on this? Yes. So I've heard about this for the past 25 years since I've been a student in manufacturing engineering, right? You can't cut on the same machine. Well, what happens if you calibrate it and you calibrate the machine, right? So you have a standard, you calibrate it against your standard, and you know that it's coming out to the right size. Another step you could do would be a gauge R&R study, right? Gauge repeatability and reproducibility study on your probe on your machine. So that's really your first step if you want to qualify any type of piece of metrology equipment out there, is you want a type 1 gauge study. That's just a gauge R study. And you look at basically the repeatability of your actual probe based off of the type of tolerances you're going to be measuring. So I'm kind of getting off topic there, but yeah, no, there's manufacturing engineering tools we can use to qualify that and basically verify that, hey, if we're inspecting on this machine and it's been basically validated with a gauge R&R study. So hopefully that helps you, Chris.
I think there's also a manufacturing process thing here of just having that, knowing that you have a quote good part coming off the machine before it even goes to inspection. You're not wasting a final inspection process because you've already gone through this on the machine. Yes, it might not be, you might not have a qualified team or machine, but at least you have a better point of reference before you send it to inspection.
That's a great point, Auburn. Yeah, definitely. So now, if anybody wanted if you have any questions, I'm going to end the session in 1 minute. But if you wanted any of the material, I would love to email it to you. My email is right down there, tgiorgio@calpoly.edu. It's also in the handout section in this webinar. But if you didn't get a chance to get it, I will definitely give you all my material. I'm out there to try to help basically build this industry up, right? CNC industry. So that's what it's all. And thank you for your time, everybody. We're going to end the recording now. I hope you have a great day and enjoy the rest of the HTEC conference. See ya.